Hi, my name is Jimmy Lee. In this talk, I will present our work Spot SDC, which is a visualization system to help analyze a program's resiliency. This work is a collaboration between the University of Utah and Lawrence Livermore National Laboratory. We are becoming more and more reliant on high-performance computation platforms for all kinds of scientific discoveries, such as weather and climate simulations, nuclear simulations, drug discoveries, and machine learning. Our passion for faster computations and large computation capacity has motivated industrial to design machines with smaller but more computation units. This computation skills has lasted for decades, and it is facing a challenge now. As the size of the computation unit shrinks and the number of computation components in a machine increase, the application that we want to run on those machines became more and more vulnerable to the error, and the reliability of the computation result becomes a concern. There are different kinds of errors that can challenge an application's output reliabilities. Errors such as truncation error, position errors, and hardware errors are well known by the application domain, and they are being studied for a while. Software is a special kind of errors that has begun to threat the reliability of the computations. Software is special because it occurs randomly in a program's execution in any location at any time without notice. And most of software errors are caused by cosmetic particle hits on chips, and these particle hits can switch the value of the transistor and lead to a single bit flight events. And these events will occur more frequently in the futures with the computation scaling threats. Researchers has been report like many software error corruption events. For example, like in Oak Ridge National Laboratories, the supercomputer Dragas has a single bit flight events every 6 hours, and the Q machine in Los Alamos has a report like 26 errors per week. And the software errors also threat the reliability of the commercial applications. And for example, in Amazon S3 data centers, they report that a machine are corrupted by a single bit flight events, and that corruptions leading to incorrect system states. And after the corruptions, a large amount of servers in the data center start to sending each other system logs and other weird behaviors. Many technique has designed to protect program from software errors. One of the most common and flexible method is a duplication technique. Such technique includes instruction duplications, component redundancy, and process replications. The main idea is the same. They perform the same task at least twice and compare a result to detect whether software error corruption has occurred. However, this method will introduce significant overhead if we want a full coverage protection of a program's execution. It worth to notice that not all computations are vulnerable to software errors. Some programs have some level of resiliency to software errors, and errors that occur during the computation can be mitigated. For example, a single bit flip that occurred in a program such as K-means or Monte Carlo simulation won't affect the program's outcome a lot, and it is not clever to have a full coverage protection on an application like that. So for design an economy method to protect a program from software errors, understand how the program reacts to the software error is mandatory. In high-performance computation programs, bit flip error can corrupt pointer variables, which will cause segmentation faults or program crash. However, a program crash shows a clear symptoms, and the problem can be addressed by rerun the application again. A bit flip errors can be mitigated by the program because program's natural resiliency to errors, and the final output is not affected. The most troubling outcome is silent data corruptions, in which an error corrupts the program's computations, and the error propagates around and affect the final output without notifications. And the domain expert used the error corrupted output to make scientific decisions. In this study, we use fault injection tool to simulate the effect of the software errors. Fault injection tool is a program that can selectively flip a bits of a program and tracking the error corrupt program's behavior. The fault injection campaign is a collection of fault injection experiments. In each fault injection experiment, the fault injection tool randomly select a bit during the program execution and flip it. The result of a campaign is a collection of programs running log and the computation outcome. Usually, the domain expert use a statistic method to analyze this log and give a high-level statistic profile of the program's resiliency. Study how error propagate around a computation will help domain expert understand why error is brought or are mitigated during computations. This insight will help domain expert answer the question of why a program component is vulnerable to soft errors and what might be the best approach to protect vulnerable components. However, there's a few visualization tool to help domain expert to track error propagations. In this work, we are tracking error propagation by monitoring the critical data variables value, and we define error by comparing the error-free ROM with the error-corrupted ROM. Our visualization system is designed to analyze this log data, and our design is guided by the domain expert's analyze pipeline. Domain expert often study different programs components SDC property and then observe how error propagate in this component to infer reason about their vulnerabilities. At the end, they decide whether this component should be protected or how to protect them based on the analyzed result. In this study, we use three different metrics: SDC ratio, SDC impact, and SDC frequency to quantify a program component's vulnerability. SDC ratio tells how likely it is an error in a component will lead to SDC outcome, and SDC impact shows how bad an SDC event will introduce error in a computation's final output. SDC frequency gives the information of how frequently the SDC event happen in a program component. In the visualization design, we utilize the natural hierarchical feature of a programs. The hierarchical visualization design enables user to examine a program's SDC property and observe error propagation with the same hierarchical structure. And the design enables user to choose different granularity of details during the analysis as a single programs or multiple functions or individual variables or single line in both type of analysis. To summarize the result of the bit flip experiments, we design a bit level visual encoding, which refers to the I340 floating point representation format. This visual encoding enables user to study an individual bit's resiliency without loss program's overview SDC profiles. The visualization here tells us that in the conjugate gradient programs for different data variables and different lines, most of the bit flip happen in the mantissa bits won't affect the program's output, and the majority of the silent data corruption is caused by bit flip in the exponent bits and the side bits. In the SDC property analysis and the propagation analysis, source code correlation is an important and the final step. As the domain expert finds some interesting pattern during the analysis, they need to go back to the source code to reason about a pattern and find out why an error corrupt program shows certain behaviors. The usability of the system can be demonstrated by a few use cases. One interesting resiliency feature of a program is how it reacts to the bit flip occurring at different time. Here we can use our visualization system to examine the impact of silent data corruptions over different computation iterations. From the result, we can tell that the impact of the bit flip will reduce with the increasing number of iterations. This effect indicates that the soft error will have more impact on a computation's early iterations than the later iteration. For injection campaign, randomly inject error into a program's computations. This stochastic process will introduce a problem that some program components do not have a balanced sample coverage, and the resiliency conclusion about that will be problematic. Our system enables users to optimize the data online during the analysis. In this fault injection experiment with the fast Fourier transform programs, we see that line 725 does not cause any silent data corruptions in the initial data, and domain expert can make a conclusion that this line is resilient to the soft errors. However, our visualization shows that the initial data has bad sample coverage, such that only the lower mantissa bit has samples. After optimizing the data with more samples added to the components, the new data tell us that the exponent bits can lead to silent data corruptions. And with this checking and iterative data optimization operations, and our system can improve the fidelity of the analysis result. The SDC help user to check the error propagation in the case that an error explode or the error is mitigated over time during the computations. Here we use the spot SDC to compare the SDC cases and the mask cases in the conjugate gradient algorithm. In both cases, the errors start to explode or reduce in the same data variable alphas, which is a variable to decide the search direction and whether the search direction is orthogonal to the previous search steps. And this information indicates that alpha can decide whether the conjugate gradient will converge or diverge, and it is an important variable that domain expert need to protect from soft error or use it to detect the soft errors. With the feedback from our visualization, the majority of the SDC come from the bit flips in the side bits, exponent bits, and higher mantissa bits. The sample from the low mantissa bit do not offer too much information about the photon analysis, but they take a large amount of sample in the fault injection campaigns. And this pattern indicates that the random sampling method wastes a large amount of computation resource on useless information. And this motivates us to propose new sampling method to understand a program's resiliency. A simple optimized method can sample like 80% of the data from the exponent and side bits, and the rest of 20% from the mantissa bits. A more sophisticated method can split the sample into like 10 steps. In each sample steps, the algorithm can use a binary search method to find the least significant bits that cause silent data corruptions. And after bits found, the rest of the sample will come from the side bits and the least significant bits. We compare our two methods with the random sampling method and use the SDC ratio and SDC impact to quantify the quality of the sample data. We use the fast Fourier transform and the conjugate gradient benchmark to evaluate the performance of different sampling method and compare it with the golden ground truths. The evaluation result indicates that both the propagation sampling method have better performance compared to the random sampling method, and the A with 2 sampling method is better to capture program's SDC impact in both benchmark, and the iterative method has a small SDC ratio standard deviation compared to the rest of the methods. Finally, I want to summarize the main contribution of this work. We create a visualization tool that enables HPC domain expert to analyze the resiliency of the programs. This tool provides a multi-level granularity of detail of a program's resiliency to silent data corruptions, and introduce a new guideline for sample the fault injection space and provide user useful insight into how error propagates through a program's computations. Thank you.